friends, welcome to video lecture on dynamics of machinery. In the today's lecture, we'll see the numericals on free damped single degree of freedom system, session number 4. So let us start. The first numerical on this topic, the mass of a single degree damped vibrating system is 8 kilogram and makes 28 oscillations in 16 seconds. When disturbed from its equilibrium position, the amplitude of vibration reduces to 0.3 of its initial value after 5 complete oscillations. Determine first point stiffness of the spring, second point logarithmic decrement, third point damping factor. So first of all, write down the given data. So in this case, the value for the mass is given. Mass m equals to 8 kilogram given. Okay. So next to this, 28 oscillations in 16 seconds. This information is given. So from this information, we can get the value for natural frequency in terms of hertz like this one. 28 oscillations. So the formula for this one, number of oscillations to the time required for the same. Time required. So Fn we can get like this. So 28 oscillations with us. So time required to complete the same with us 16 seconds. Okay. So if you do the calculation for the same, you can get 1.75 hertz. Now, if you want to get this value in terms of omega n, okay, frequency in terms of radian per second, then we know this relation 2 pi into Fn. So from this relation, we can get omega n equals to 2 pi multiplied by 1.75. Okay. So after doing calculations, the value for this one we can get as 10.9956 radian per second in this way. Now next to this, once the frequency is calculated, our next task is very easy to get the value for stiffness. So we know omega n equals to square root of k by m. This relation already we know. From this relation, so what's about the value for omega n? Already calculation done by us for this one. So substitute the value for omega n here, 10.9956 equals to square root of k by m. If I remove the square root sign, then you have to do the square plus both the side. Okay. So in this way we can get the information. So already the value for the mass with us 8 kilogram. Just substitute here. Okay. After solving this, what's about the value for the k? K can get as 967.22 Newton per meter. This is about the value for the k. Write it here. So this is the answer for the first point. Now, to get the answer for the next point, we know the logarithmic decrement. The relation for the logarithmic decrement is as like this one. Second point, it is about the first point. Logarithmic decrement, that is delta equals to 1 upon n log to the base x naught divided by xn. in this way the relation with us. Now, what's about the information given in the problem? The amplitude of the vibration reduces to zero point 0.3 of its initial value after 5 complete oscillations. Okay, so for that, if I consider x naught, let x naught be the initial amplitude and next one after completion of 5 oscillation, I'll just say x5 be the final amplitude. So once we assume this one, then already this relation with us. Okay, so if you draw the diagram here for displacement versus time, we can get this response like this one. So the amplitude we have assumed as initial amplitude here is nothing but the x naught. Okay, so after some time the amplitude get reduces like this one because of the damping present in the system. So what's about this one? This indicate the x1 amplitude, x2 amplitude, and that will continue up to xn. So in this case the 5 complete oscillations, okay, we have to just consider up to 5 complete oscillations, means xn value is nothing but here 5. So equation number 1, this one, the logarithmic decrement delta will changes like this one. So delta is nothing but 1 upon n, means in this case 1 upon 5 log to the base e x naught by x5. So very important relation is given here. The amplitude of the vibration reduces to zero point 0.3 of its initial value after 5 complete oscillations. Okay, so what's about that relation? So simply we can write that relation like this one. So 5 complete oscillation, whatever the amplitude after completion of 5 oscillations must be equals to 0.3 of its initial value. So initial value with us x naught. Okay, in this way. Now this equation, this one, this relation for the logarithmic decrement delta will changes like this one. 1 upon 5 log to the base e x naught divided by xn. So what's about this xn? Xn is nothing but the x5. X5 for that relation already with us 0.3 into x naught like this one. Now here in this case x naught get cancelled. Okay, so solve this. So in this case we can solve like this one. Say 1 upon 5 as base is given here e, means you have to just press this button. Okay, so next to this one x naught here get cancelled. So what's about here 1 upon 0.3 will remains. Okay, so complete the bracket and get the value for delta. So what's about the value for the delta? After doing calculation, the value for the delta with us, therefore delta equals to 0.2407. In this way the value for the delta with us. This is about the answer for second point, logarithmic decrement. So we'll move towards next. Our next target to get the answer for damping factor. Damping factor, okay, that is zeta. Okay, so already I have seen this relation during the discussion of significance of logarithmic decrement. So during that small experimentation discussion, already I have seen the relation between this zeta and delta. Okay, that relation is like this one: zeta equals to delta divided by square root of 4 pi square plus delta square like this one. So the already value for the delta with us substitute here and easily you can get the value for zeta. So what's about the value for delta? Delta with us 0.2407 divided by square root of 4 pi square plus delta square means here 0.247 square. Okay, solve this, get the value for zeta. Now solve this for zeta. We know this one, this relation already with us. So delta value already substitute here. Okay, substitute here and delta okay here. Then get the value for this zeta like this. Just press this button. Then found the value for zeta as 0.0328 means here this one. The answer for third point. I hope this concept clear to you. So whatever the, just say once again steps to solve this problem. Okay, stiffness of the spring, just get the that value with the help of natural frequency relation, that is omega n equals to square root of k by m. Then to get the relation for this logarithmic decrement, we know the relation delta equals to 1 upon n log to the base a x naught divided by xn. So whatever the initial amplitude and final amplitude, a relation is given. Okay, try to write that relation, try to draw this diagram like this one. Okay, see the initial value and final value. So whatever the complete oscillations are given, that is nothing but the value for n. To solve this, okay, so get the value for delta. Once you get the value for delta, easily you can get the value for zeta. Okay, so these steps always almost actually remains common for the problems related with this one, stiffness, then logarithmic decrement and damping factor. Okay, so very easy. So next problem, take this problem for practice. Okay, so the mass of a single degree damped vibrating system is 7.5 kilogram and makes 24 oscillations in 14 seconds. When disturbed from its equilibrium position, the amplitude of the vibration reduces to 0.25 of its initial value after 5 complete oscillations. Determine the stiffness of the spring. Second point, logarithmic decrement and damping factor. Almost carbon copy of the previous problem. Okay, just follow all the steps as it is and get the answer. I'll just give the answer here. Okay, practice it. K equals to 870.1 Newton per meter. Answer for the second point. Delta equals to 0.227. Third point, zeta equals to 0.044. Let us start next problem. A mass of 1 kilogram is to be supported on a spring having stiffness 9800 Newton meter. Damping coefficient 5.9 Newton second per meter. Determine natural frequency of vibration. Also find logarithmic decrement and amplitude of 3 cycles if initial displacement 0.3 centimeter. So first of all, just write here given data and see you have to do calculations for what. Okay, so here in this case our aim is to find out the value for this one omega n, then amplitude after this one 3 complete oscillation. Okay, so here in this case the value for mass with us 1 kilogram, then value for stiffness is given 9800 Newton per meter. Then next one, the value for damping coefficient is given 5.9 Newton second per meter. Okay, so don't mix up this term. C with the zeta. Zeta is nothing but the ratio, damping ratio and C is nothing but the damping coefficient. Okay, so next part is nothing but can easily get the value for this omega n. Okay, so what's about the omega n? The regular formula with us, square root of this one k by m. Value for k with us 9800 by mass with us 1 kilogram. If you solve this, you can easily get the value for omega n equals to 98.9949 radian per second, like this. Now next target is to get the value for logarithmic decrement. Okay, so logarithmic decrement, so we know the relation for this one. So in the previous problem, already I have seen the logarithmic decrement delta is nothing but 1 upon n log to the base x naught divided by xn. But this relation is applicable when the value for this one initial amplitude and something relation between this one final amplitude is given. So in this case, if you just say the information regarding the 3 cycles, okay, so the value for the this one n with us, but if you look towards this problem, the damping coefficient is given. Mean certainly the terms related with the zeta indirect, you have to just take the relation for that zeta into consideration. Okay, so we know this one, a relation between delta and zeta. Zeta equals to 2 pi in, sorry, this one delta equals to 2 pi into zeta square root of 1 minus zeta square. You look to us earlier, we have studied this relation. Here we have studied that relation. Okay, while discussion of logarithmic decrement, that is delta equals to 2 pi into zeta divided by square root of 1 minus zeta square. Okay, so from this relation, so here is that relation. A logarithmic decrement delta equals to this one 2 pi into zeta divided by square root of 1 minus zeta square. Okay, so in this case we know the relation for zeta. So what's about this zeta? Zeta is nothing but ratio of actual damping coefficient to the critical damping coefficient. So the actual damping coefficient, the value for the C already given in the problem. Okay. So what's about the CC? CC we can get from this relation 2 into m into omega n. Already I have seen this relation while the discussion of free viscous damping. Okay. Now see this one a relation. This is the relation already I have seen C equals to 2 into m into omega n. Okay. So this relation is derived from, okay, this one basic free vibrations with viscous damping. Okay. So once we solve this one step by step. Okay. So in one of the step already we have defined this one zeta term. Zeta is nothing but it is the ratio of actual damping coefficient to the critical damping coefficient. Okay. In the previous step, if you just see the critical damping coefficient, Cc is nothing but 2 into m into omega n. This relation already with us. So by using this relation, easily we can get the value for this one Cc. So Cc is nothing but 2 multiplied by m with us 1 kilogram multiplied by omega n. Already calculation done by us for the omega n, that is 98.9949. If you simplify this one, you can get the Cc is nothing but 197.9898, like this one. The unit for this one is nothing but Newton second per meter. So another name is also given for this one as force per unit velocity. If you just say the force, we can measure in terms of this one Newton, and per unit velocity, the unit for the velocity we know meter per second. So this one goes in denominator, okay, means we can get this one force per unit velocity, okay, another name given for this one damping coefficient, okay. So once we get the value for cc and c, next task is very easy. So get the value for zeta. So zeta is nothing but, as per our discussion, c divided by cc. Substitute the value for c here. The cc already calculated by us 197.9898. Okay. So after simplify this term, we can get zeta equals to 0.0297. Okay. So already the delta, this term with us, give equation number 1 for this one. We just substitute the value for zeta, substituting zeta in equation 1, can get the value for delta. So delta equals to 2 pi, zeta with us 0.0297 divided by square root of 1 minus zeta square, means here 0.0297. Look towards this equation to the square for this one and get the value for delta. So delta equals to 0.1857. Here is the answer for next point. Okay, so here we found the answer for the first point, natural frequency of the vibration. Also find the logarithmic decrement and amplitude. So this is the third question. Okay, so we'll just solve that point here. Also amplitude of 3 cycles if initial displacement .3 centimeter given. Okay, so for that we know the relation. Once again, delta we know 1 upon n log to the base e x naught divided by xn. This is the relation with us. Okay, so here the value for this one, my aim is to get the value for amplitude corresponding to this one third cycle. Okay, so in this case, since the value of n with us 3, delta already calculation done by us for this delta. Okay, so delta is here, this one. So we can just rearrange this equation in this way. N into delta, okay, I'll just take this n here, equals to log to the base e x naught divided by xn. Okay, so in this case the value for n with us 3, just substitute here 3 multiplied by delta. So delta with us 0.1857 equals to log to the base e x naught by xn. X naught by xn means here x3. Okay, now just simplify this one like this. Here the value for this one given 3 centimeter. Okay, 0.3 centimeter. Just convert this one into meter. Okay, so 0.3 centimeter is given for this one. Initial displacement is given, means here x naught value, since x naught is given 0.3 centimeter. Okay, you convert this into meter, you can get like this one. Once again, if you see towards this relation, okay, log to the base e into x naught by x3. This is the relation with us. My aim is to get the value for x3. Okay, so here if I take the anti-log, then what will happen? X naught by x3 equals to e raised to, so what's about this one, n already with us 3. Okay, multiply by 1757 like this. Okay, what's about the value for this x not given? 0.3 centimeter. Already we have converted this one into meter like this one. X3 equals to e raised to 3 multiplied by 0.1857. Simply solve this one. Okay, so here x3, our target is to get the value for x3. 0.3 into 10 raised to minus 2 divided by e raised to 3 multiplied by 0.1857. Okay, solve this one here. 0.3, be able to see this one. 0.3 multiplied by 10 raised to minus 2 divided by e raised to, means you have to just press this button, and this one e raised to 3 multiplied by 0.1857. okay, just press this button, you can get the value for x3 equals to 1.7186 into 10 raised to minus 3. Okay, in terms of meter, this is the answer for next point. In this way we can get the answer for the next point.